evening, everyone. I am Apurva. Um, I am a PMRF PhD student in IIT Bombay, and I'll be taking the second week's tutorial as well. I'll quickly revise what we talked about in week 1, just the big picture. If you have doubts, you can stop me. Else, we'll just move on to this week's uh, lectures and some problems from there. Okay? So, last time we started by talking about what exactly the word control means, what stochastic control means, that it is just decision making under uncertainty. And we try to understand what is risk and what is information, what is the role of these two in stochastic control. We saw that in case of problems like this, whether a cake is to be directly bought or a lottery is to be bought, and at the end of that we may get some amount of cake with some probabilities. So in this particular example, the source of randomness was in W1 and W2, and that was coming out of the lottery itself. Then we saw here it makes sense to take the average decision, and hence it makes sense to actually pay for the lottery because there is a possibility of getting more cake with the same pay. But if we scale the problem, for example, if instead of the token money for the lottery or directly it was a bigger amount like 1 crore for getting a house, then the probability of losing the house, not getting anything in return, even though we would have bought a lottery, is quite large. And hence, it's riskier to take the lottery. And we saw this concept comes about naturally depending on what approach we're choosing to define the outcome. So one option was average, like in case of this cake type lottery. Another option was looking at worst case outcome. One more possibility was looking at the best case scenario. But all of these can come in one theory together, and that is called utility theory. And to talk about utility theory, we need this conditional probability. This is the probability on outcomes. See, it is talking about when the outcome that depends on the decision and the particular state is equal to some OI given a decision, then what is the probability on such outcome OI? That's what it is referring to. And we saw what it means in the specific case. Then we saw that there is a theorem which says under some assumptions, there are specifically 4 assumptions, there exists a function u that takes us from the outcomes to real numbers, and it gives us a preference ordering. And it says if the preference ordering between decision d1 and d2 is such that d2 is preferred over d1, then the probabilities of d2 for any particular outcome compared with probabilities for d1 for the same set of outcomes would have the same preference ordering. And this also implies that the expectation of this utility function for the outcome would also have the same preference ordering. Meaning, if we can find out what this is, if we can find out, since this is a minimization problem, if we can find out which outcome or which decision minimizes the expected utility, then we know what should be the ordering in the probability distribution on the outcomes, and also we know the ordering in case of the decisions directly. And we saw a couple of examples of this. We saw what it means to actually take an example utility and work with it. And we saw 2 important conditions for any such utility is that it should be concave and increasing. Increasing because we want the preference ordering to sort of stay the same, to be a monotonic thing. And concave because it ends up giving us a risk aversion. It gives us something that is risk averse. It minimizes the risk as much as it can. So we saw a few examples of that. these were the assumptions between preference ordering, between two preference ordering, or between P1 and P2. If they're equal, what happens to the mixture of them? If they're not equal, then what happens to the mixture of them, and so on. And then finally, we talked about sequential modeling. If the information was available in sequence, or if the whole process is a sequential decision making, which means this is the random quantity, u0 and u1 are the controls or the actions or the decisions, x1 x2s are the states. So there are two possibilities, there are two possible cases here. One is if u0 and u1 are to be chosen at the same time. That's case number one. Another case is if u1 and u2 are chosen in a sequential manner, meaning u0 is chosen first and then u1 is chosen. And when u1 is chosen, x1 is already realized. This much is already realized, meaning to find out x2, all that is being done is to figure out what is u1, and that's all. And hence this u1 can be something that depends on x1 itself. Point being, it's the way the information is available that allows how the control can be taken, and that possibility of having better control can end up giving a situation where the minimized quantity, whatever we're minimizing, could be different depending on the information available. And we saw this in case of one more example. Now today we're going to talk about these types of sequential decision type problems in a more formal setting. We'll mostly be spending time going through the formal setup and look at one or two examples which, apart from the one that was there in the lectures, we'll just look at a few more examples to see how it fits. Okay, so is that all right? Any doubts from what we talked about last time? Okay, so I'll continue since there are no questions. Okay, so like I said, in today's lecture we are going to talk about sequential decision making, and we are going to specifically talk about the model that describes it, and this model is called the state space model. This actually has a few different ways of looking at it. One is the way people in stochastic control look at it. Typically, control community is interested in minimizing some loss, some cost. On the other hand, the other community, which is the one that looks at this decision making under the framework of Markov decision process, tends to maximize the reward. Instead of a cost, they have a reward, and that's what they're trying to maximize. So it's possible to map these two problems to each other, but they have slight differences also. So I'll go through all of these things more carefully. Stochastic control and the framework that I'll start with is the one that is typically dealt with by the control community. On the other hand, this MDP type setup is the one that is either used in operational research or even people in CS use it. So those of you who are coming with reinforcement learning as your motivation to do this, MDP is the key word, the key terms, the key formulation that you will be focused on. Okay, so in this particular lecture we're going to talk about the situation where time is discrete and we are taking a horizon for it, as in our whole process continues only for a limited number of steps. So let's say we have a step count also. So let's say we have n steps. So let's say k, time is denoted by k. It starts from 0 and it goes till n minus 1 steps. Okay, in these steps, so at each step there will be a few quantities that we'll have to define. These quantities are x of k, which is the state of the system at time k, then uk refers to the control or the decision or the action, again at time k. wk is the source of randomness in the problem. So it's going to be something that is given by nature itself, and this is the one that is available at time k, meaning at different time scales we are allowing the randomness to vary. Just like in the previous lecture we had w1 and w2, it's the same kind of thing. And we have a horizon for this, or total number of steps, so that is what we call as time horizon. Now when people talk about the stochastic control way of formulating the problem, they have a dynamics from how to go from state xk to state xk plus 1. So there is some function, let's say it's f of k, which takes in the value at the previous state, then it takes in whatever control was taken over there, and also the randomness in the setup. Okay, so this is the core setup that stochastic control talks about. This is the framework when we are talking about stochastic control. Any doubts so far? Okay, let's continue. Now here the goal is to minimize some quantity. So in the minimizing process, let's say we are using a function g. We are taking g of n of some x of n. Note, we are starting from step k0, but we are going till n minus 1. And we are saying that there is one more extra state. We are referring to that as x of n, which is typically called the terminal state, because this is where our process ends. I'll show a small diagram and show what this means eventually, but for now just take it this way. And also it's going to be a sum over all the other gns. Okay, this is a very general setup. The cost may or may not depend on all of them. It may just depend on xk, it may just depend on xk and uk. In the most general case, it will depend on all the parameters at time k. And since there is a source of randomness here, which is wk, we'd be more interested in taking the expectation over this. So it is this quantity that we are interested in minimizing. So here this gn is the cost for xn, which is what we are calling as the terminal state. Okay, now there are two ways of dealing with this type of a problem. If our goal is to minimize some expectation quantity, there are two ways of dealing with it. If you notice, yeah, so if you notice, for us the only parameter that we have in hand is going to be UK, the action or the control or the decision. Now, how is this chosen or how is the control chosen is something that defines everything for us. We saw there are two ways of doing it in the last lecture also. One was if UK, all the UKs are chosen at the same time and we are not bothered by what XKs are. That is one possibility, and that is called the open loop version or the open loop problem, where U0 till UN minus 1, all of them are chosen at the beginning. At the beginning and without using any information. Without using XKs. On the other hand, closed loop means if UK is chosen using XK, or it doesn't have to be XK specifically, it can be the history also. Sorry, chosen using so in such a setting, history means let me denote it by HK. So history means whatever is known up till this point. So that would include the 0th state, the state where the problem would have started from. Then whatever action was taken at that point. Actions are denoted by U here. Then the next state, then the action after that, and so on until one state before. So one state before is XK minus 1 and UK minus 1. This much would be known. But at the same time, UK is to be chosen, but XK is still known. This would be the history HK. So this just means that UK is actually some function. Let me use a different symbol here. Okay. Of either XK or UK is a function of the history HK. These both have different names. Just one second, let me give the names and then I'll come back to you. This, because it's only depending on one action, one state, this is typically called Markovian. Here, because it can depend on the whole history, this is history based. Action. There's a slight catch here. I'll come back to that in a little bit of time. Yes, what is the question?
Okay, in this model, an open loop problem, we don't know anything, so we just choose before that and we'll follow it. In closed loop, when you define history at particular k, why not omega 0, omega 1 is in history? Because that also I know already.
I'll not know the exact value of it. What I'll know is going to be x's.
Okay.
I'll not know. See, here we are assuming we know this dynamics carefully. It is possible that even after knowing the dynamics, WK is such that it could have taken multiple values and still given us the same xk plus 1. So it may not be possible to deduce WK completely.
Okay.
That's first point. And second is, here the ordering is this way. Just one second. Yeah, the sequence of how this is followed is as here. Okay, let me draw here. So what happens is at any time interval k, okay, at time interval k, this much has already passed, so this much information is already there. Okay, HK amount of history already exists. After that, meaning here we have some XK, after that an action is chosen, After the action is chosen, the value of wk is realized.
So basically,
And
we
then
can't
the
measure
next one
omega k
comes
all
up.
the time.
Sorry?
So we can't measure omega k all the time.
Not all the time. It depends on
Oh,
the specific details of the problem, but many a times it's not possible.
okay, okay.
In fact, wk, this one, the one that comes after you're choosing uk, that will not know for sure. So there is some amount of randomness at any time step when action is to be taken.
Correct, correct. At the
The
UK
previous
level,
one, we
yes.
even if we know, it's not making any real difference, right?
Okay.
And hence, I would say it doesn't make sense to try and deduce what those previous wks were, unless the point is to get a distribution out of them and then use that information further. If all of that is
Yes,
being
yes,
done,
yes.
maybe that's possible,
Yeah,
but
because in data
typically,
analysis, similar kind of thing, we try to reduce omega k somehow.
hmm,
Yeah,
it's
yeah.
possible, but
Thank you.
it may not be needed in the general framework. Okay.
Yeah, okay. Thank you.
Yeah, sure. Anyone else, any doubts so far? Okay, then I'll continue. Okay, next thing is the inventory control problem that was talked about in class. Okay, so I'll go through the main points again, and we can talk about the different variations that are possible within inventory control. Maybe one or two minor variations we can talk about. Okay, so inventory control is a kind of example where you can think of a retail store. There are some objects that are being sold, so there must be some stock of those items. Then every time a new customer comes, some amount is going to get sold out, and hence the inventory is going to keep reducing. And at the same time, after every set amount of interval, uh, new inventory would be ordered. These are the items we need, and we need them in so and so quantity. So there'll be some amount of orders placed. So that orders that are placed are termed as the actions for us. So this is the stocks ordered. So now here the time interval is actually important. So think of it this way. This is the kth time. Whatever we are talking about is before it happens. So maybe before the store opens tomorrow in the morning, whatever I'm talking about is maybe night before. So that's what before k means. So stock ordered before the period k, before time k. And xk refers to the stock available at, or rather before k. Okay, here, see, if we were to make a proper model of how retailing works and how inventory control is to be done, we should be keeping a delay in mind. How much time will it take for the order to arrive? And there might be a randomness in that also. But for the simplicity of the model, what was assumed was the delivery is immediate. So whatever is ordered reaches almost right away. And the only source of randomness is the demand, because that we can't tell what is happening at any given point of time. Demand, or whatever the stock that is being purchased at the time k. Since it's wk, it means that there is some w0, w1, and so on till whatever time period we are focusing on. Let's say we are focusing on time horizon n. So we have till n minus 1. Now here again, in our model we have a choice of defining how the demand is happening. right now, for the simplicity again, we are assuming that all of these W's are independent. We could be more specific about it. We could say that these W's are IID sampled from a distribution, or they're actually coming from a they're coming from a Markov chain, meaning it's like saying, so if in a retail store we see the number of customers is more, the chances are people would be tempted to go there and try. On the other hand, if a store is almost empty, even though it might be a good one, but if it's almost empty, other people who look at it may not go there. So demand may also be something that depends on what is already there. So now I'm thinking of demand in terms of number of customers which are visible in any given store. So it depends how we want to model the problem. It can be in more than one ways. Okay. Then now again, the sequence, the way this problem is working is, first there is some xk which is available, some stock which is available. After that, the number of stocks which are available would be known. Someone places an order, so uk amount of stocks are ordered. After the order has been placed, meaning in some sense when the store opens and the customers start coming in, once the customers start coming in, let's say they're coming between time period k and k minus k plus 1, there's still time here, even though we have discretized it in such a way that we are focusing on k and k plus 1, but in the continuous sense there's still time there. So there could be a number of customers who show up. So the demand could be fragmented, could be separated, could be queued during the time duration, which is what it means that wk will be known after we've already taken the action of ordering inventory. Then this wk will be realized, or the demand will be realized, and this loop continues to go on till we reach the horizon. Once the horizon is reached, at the end point it's just xn. That's it, it stops at xn. That's the stock available, and there is no more order placed and no more customers coming in, no more demand. That's when the store maybe closes. Now the problem that was discussed in the lectures also had an assumption that there is no that backlogging is allowed. What do you think the word backlogging is allowed means?
Maybe if we missed, so we can deliver later. The next time step we can deliver.
Yeah, backlogging allowed means in a slightly mathematical way, it just means that xk can be negative. That whatever extra was ordered but not used up in the demand can still be stored. So there is a storage facility option available, and all of that can be also done. Another way of thinking about it, if the available stock plus the ordered stock, the total xk plus uk was less than the demand, then that negative is also noted down and next time extra is purchased. So in that sense, backlogging is allowed. So if the situation is that backlogging is not allowed, what does that mean?
Maybe xk will be clipped to 0, cannot be negative.
Yes, xk gets clipped. It can't be negative. That's all it means. Okay, further on in this example.
But just to, sorry to disturb, but
Yeah,
I have this curiosity. Here I am somehow imposing, the problem is imposed in such a way that every k instance decision has to make. Correct? Because the problem is like that, it makes sense like every k instance somebody has to take decision. But is it necessary? Like every K instance, somebody has to take decision. Maybe it's a randomly K chosen points. Somebody has to take decision. In that case,
Okay, so in this particular example, we are not saying that UK has to be always greater than 0. Right? UK can be 0, which is as good as saying that no order was placed, which is as good as saying no no action was taken. So that can happen, but that in sequential decision making, what we are trying to say is UK is something that depends on XK. Now, if XK is such that no action is required, then sure, no action is required. That no action required could be either staying in the same state, so like adding nothing to it. So, if you were to think of it in terms of a Markov chain, it's like a self loop allowed. You can stay in your same state. But staying there, even though you're not doing anything is also an action, right? So you can still put it in the same framework and be fine with it.
okay.
Yeah. All right. So in this particular example, the cost was given in the following way. There are three terms in the cost. The first one is a cost that depends, more like a penalty that depends on your xk. So let me elaborate on this. What does this mean? So this r of xk is more like a penalty. So if xk is positive, meaning that there is a lot of stock that is still available, then there has to be some kind of a storage cost. So there could be a storage cost when xk is positive. On the other hand, if xk is negative, then the retail, the store is losing customers. So it will incur some cost because of lost opportunity, lost sales and revenue. So that also comes up as a penalty. Okay, so it depends whether xk is positive or negative. It can be defined in any particular way, doesn't matter. But here, this is all it means. Okay, maybe you can move this a little bit lower and discuss it in more detail. Okay, so this was one kind of cost. The other kind of cost is now if some stock is to be ordered, there will be a price to be paid for each of those units that are being ordered. So UK, since is giving us the number of new items that are ordered, C refers to cost per stock or cost per item. It's possible that this C depends on, it doesn't depend on K, but it depends on the number of UK. That is also possible. So that could have been just, this could have been converted into a normal function. This is trying to say that if the number of stocks that are being purchased or ordered are less than a certain threshold, maybe you have to pay a higher per order cost. If they are beyond a certain threshold, maybe you have to pay a lower cost. So it's like a wholesale idea. If you're buying in bulk, you might get it slightly cheaper and all of that. So that could also be modeled in this cost itself. Okay, and now, like I said earlier, apart from cost, or apart from having each of these individual cost, there would be a cost even for the terminal state. This is like saying whatever inventory is still left at the end. Maybe the store reaches a situation where it needs to close down completely. Then, if there is still some stock in the inventory, some positive stock, then that means it still needs to take care of that. It needs to try and either sell it or try and do something about it. That stock is still lying around. So there might be an extra cost because of that. Okay, so this was the problem setup. Now, just like we talked about earlier, in any of these situations, we have to talk about open loop and closed loop. So, open loop strategy would mean placing order u0, u1 until un minus 1, placing all of these orders without looking at the inventory, without looking at the number of stocks available. So, just ordering them randomly or without using xk. On the other hand, in closed loop strategy, all of these UKs would be based on some function. So I'm using this mu to refer to the function, and that function, let's say, depends on xk. Whatever is the inventory, whatever is the number of stocks right now. I do not care about the stocks in the previous time step because those would have been already taken care of in the previous demand and previous cycle. Whatever I have remaining right now is all that matters. So this is also one way of going about it. So this is called the closed loop strategy. And this particular course is actually going to be mostly focusing on closed loop strategies itself. Is that okay? So this is the problem setup so far. So now we can make a small diagram to depict whatever is happening here. This diagram specifically focuses on the closed loop strategy, okay? So here we have the number of stocks available xk. This stock affects the inventory. This also is something that affects the cost. Another thing that affects the cost is what is ordered, the number of stocks that are ordered. So for that we have UK, what is ordered at any given time interval k. And then after all of this is ready, and when the store opens, let's say the next morning, the demand comes, and that demand that comes is WK. This comes in the period K. So what it means it comes in the period K is, so let's say we're starting at K and we're looking up till K plus 1. In this duration is what we are referring to in the period. The previous ones would have been taken care of, dealt with in the previous time periods. Then as a result of all of this, we'd get to know what is the number of stocks available after this time period is over, and that, since backlogging is allowed, would just be the sum of xk plus uk minus this wk, which was the demand. So see, just like we were saying earlier, the evolution of x from xk to xk plus 1 is happening because of a fixed function. It's a deterministic simple function that is telling us how it goes from xk to xk plus 1. If wk is known, in that sense it's deterministic. If wk is not known, then there is some amount of randomness, but the form of the function is not changing. Okay, and here again the goal is to minimize. Okay, let me erase this. I'll come back to this point again in a moment. Yeah, so in this inventory control problem, the goal is to minimize the expected cost, the expected overall cost. So I've written the cost terms. These are for the regular states. This is specifically for the terminal state. Now, what we have in control is these UKs, the actions or the decisions. But if you look at the problem, the way this problem is set up, it's not telling us to choose an inventory using xk. There's no conditional dependencies here. Here, we're looking at the expectation overall. We're not looking at given this, choose the next UK, given this, choose the next UK plus 1 and so on. So here, in the process of trying to minimize this particular objective, it is not asking us to minimize individually these actions. What it is actually asking us to do is come up with a plan, and that plan is the one that should minimize this, and that plan is nothing but the one that gives us the form of UK. So that plan is some function mu k that depends on xk. It's like a contingency plan. So if I had 50 stock available in my storage, I will order only 10 more. But if I had 38 only, then I'll have to order accordingly. So this plan telling me if I had this much, what will I order? If I had this much, what will I order? This could depend on time. At a given point of time, I have seen that the demand is actually reducing, and I expect for the next few days the demand will continue to reduce or will stay roughly in the same range. I'll not order much. So there could be a dependence on time as well. Okay, so this particular problem is actually trying to find the strategy, not just the action. Action are UKs, but UKs are chosen knowing XK. It's not coming up with a function. On the other hand, strategy means we're coming up with a plan. It's like a plan of action or a contingency plan. If I get this many XKs at kth time period, what will I do? What should I do? That's what strategy means. Is the difference clear between what is an action and what is a strategy, and why is this particular objective function focusing on strategy? Why is it trying to work with strategies and not just actions? So in such a situation, what I'll be minimizing over will be these functions itself. So it will be u0, u1, sorry, mu0, mu1 till mu n minus 1. It is for each time step coming up with the correct function that tells us how to deal with different type of stocks, different availability of stocks. So there's some terminology here. This whole set, at times it's denoted by this type of a symbol pi, and it is called a policy or a control law. While individually, these are called decision rules or strategy. Is this okay so far? Yes. Yes, Mayuresh.
Hello. Yes. In this minimization function, this capital R and this small r, that summation, we are minimizing the risk, right? Kind of.
R is something like a cost function. The only reason I have a capital and a small is to remember this is dealing with common states. This is dealing with a special state called the terminal state.
Okay. And we are taking here action plan instead of actions. So action plan at each time step k at it should be the same, right? At each time, if our actions will vary at each time, but our action plan will also vary. Then
Yeah. So there could be variations, right? So one of the examples that Sir took in class was something like this. Let's say mu k is so let's say we choose a threshold that if xk is less than some value sk. So this is something that depends on the time period. Okay, this could have been something like a global constant also, but for now I'm taking it to be dependent on k. Then my ordered stock should be sk is greater, so sk minus xk, meaning this. So this part means I'm trying to keep the total stock, the currently available and the one that is ordered, the sum of that to be equivalent to sk. That's what this example function is trying to do. Else, if this is not the case, meaning if xk is equal to sk, then we're fine. Then we're not doing anything. Then we're not ordering anything extra. So what will happen is this sk could differ depending on which time step we are talking about. See, like I said, this wk is something we don't know. The randomness, the true randomness, is something that we don't know, but we might have created a belief about the randomness, that we might have seen for the past 3-4 days. We are seeing that the number of customers who are coming to buy are reducing for some reason. Maybe a new store opened right in front of ours, something like that. So we expect not much demand all of a sudden, and hence we might reduce the value of sk for the next few sessions. So in that sense, there
okay,
is a dependence on time.
okay,
Okay, so if you were to draw this, um, like up till here, the demand is continuously increasing. Okay, with that in mind, what I start with is, let's say sk is chosen to be this value. So this is a bit rough. At the next time step, I expect the demand to have increased a little bit more, and hence I want there to be some surplus in my inventory. That is okay, but it should be able to meet the demand. So what I'm saying is, let's say the sk is increased slightly. So what will happen is, when demand comes, it will reduce, the stock will get expended, it will get used up, it will be bought, and then again with the next action, I'll increase the order, and I'll make it reach some other value sk plus 1, and I'll keep doing that until for some reason I realize that, oh, I don't expect any more demand from next day onwards. Something happened in between, and for few days we saw the demand itself was decreasing. We expect similar behavior, so we'll not suddenly give a spike to the sk value at that particular k time step. We'll keep it sort of steady. So in that sense, the time period does come in the picture. The situation where this time period k is not coming in the definition of the policy itself, or the definition of the strategy itself, there's a special name for it. Those type of strategies are called, you people know it, what are such strategies called? If the form of the function u0 was equal to u1 and so on, if all of these were equal, what will I call these strategies?
Stationary.
Exactly, we'll call them stationary. So stationary is possible, but if we want to model the system as close to the real world, stationary may not be enough.
But I have this following question. Let's suppose I'm the owner and I decided I'll keep maintain SK as a total inventory. Suppose, then isn't it it's a open loop problem, because I don't care about what state I am. I'll just maintain stock at a particular state. Like for example, capital SK, I want to maintain. So whatever I'll subtract and do.
So
Here, it seems like an open loop thing. There is no closed thing.
okay, in this particular example, you are using the value of xk and maintaining your sk. Without using your xk current stock, you can't maintain a certain level. You need to know what is the current stock. Only according to that, you will add or remove.
Yes, correct. But the capital SK is decided before the inventory started. Suppose I thought, let's just shoes example. So I want to maintain 1,000 shoe stock. That I decided way before my shop open. Okay.
Sure.
And small SK is something which is my current month stock available.
Sure.
So this capital SK somehow leads to open loop decision, right?
No. Open
No.
loop decision would mean UK is not something that's dependent on xk. There is dependence. If you want to maintain a certain threshold, you'll have to keep looking. Is it reducing? Is the stock that is being sold off changing with time? What is the stock currently available? Only then I'll try and maintain it at a certain level. Means whatever I'm ordering. Okay, so closed loop or open loop is on the UKs, on the actions. What I'm ordering is dependent on what is available. Unless I'm looking at that, I might have an extra surplus and I won't even know. So it's not open loop, it is still closed loop. Here, the only thing that's happening is if you keep your SK to be a constant and not let it be a SK and rather just some sort of a S, then you just have chosen an extra parameter for your problem. That's about it. That extra parameter is chosen irrespective of current demand or fluctuations or your current stock. That is okay.
Okay, so
That
like
doesn't make it open loop. Open loop
okay,
would be if this action UK was independent of XK, was chosen without looking at XK, was chosen before it even knew the realizations from the previous step. It was just chosen in the beginning itself.
Okay, so basically I can up and down my SK like with this as a function of omega k minus 1. Okay. Yeah.
Okay, so what did we talk about? We looked at this example. We looked at the example of inventory. Now, while going through this example, I talked about different variations that are possible. We can model whatever variation we want in the problem according to our requirements. We can specify what the time period even means. Does the time period mean 1 day? Does it mean 3 days? Does the time period also is something that's not the same? It's not a constant. That UK is something that is not ordered every 1 day, 2 day, 3 day, whatever. That fixed number of periods, fixed number of interval. That could vary. That could vary depending on the demand. All of that is fine, and all of that can be modeled in this current setup itself by making certain assumptions or removing certain assumptions and making it more precise. So even though this is just one example, the number of variations that can be played around with this are huge. Again, cost, this type of a cost is just one version. You can have cost which is coming up in various forms. Okay, now let's go back to the general version. So in the general version, this is what we had, right? We were trying to minimize some cost gk or some gn. You're trying to minimize all of that. And again, here also we have the same question. In this minimization process, are we focused on each action at a time, or are we focused at the whole function given whatever xk's are available? So again, the question of action versus strategy comes up. And here, same argument as before, we'd be focusing on strategies. So strategy means we are looking at the xk value. So let's say the xk values are from some space S, and using those space values we are choosing our action. AS refers to the actions corresponding to this particular state S. So this is small s. And if I am talking about the whole space, then I'd actually just take a union of all of them. Okay, so this is a function. So that's why we were earlier writing this as u of k taking xk as the parameter, and this was giving us the action uk. And we knew that action uk has to follow certain constraints of whatever is the problem. It should lie in the action space of xk. Xk is the state that we are referring to. That's why I've written it out explicitly. This part, that the action should lie in the action space of the particular state, is captured using this symbol also. So this u tilde refers to the set of all feasible actions for the state xk at time k. Meaning, whatever action we are talking about, whatever is the action that is being taken, so this one, it should lie in the feasible set, and that feasible set could be denoted either this way or this way. For us, in our previous example, you recall, okay, let's go back to the previous example one more time carefully. We had this dynamics. This was xk plus 1 was some function of these three, and we knew the exact form since we were talking about the case where backlogging was allowed in inventory. Then this was xk plus uk minus wk, where this wk was the noise, and we had this constraint. Whatever is being ordered, even though we didn't say it in our description of the problem, this constraint was straightforward. The constraint was that the value of uk has to be positive. It can be 0, that is okay, but it has to be a 0 or positive value only. Meaning the feasible set of actions for any given xk has to satisfy this constraint. And this, if we were to look at all of these, that would give us the feasible set of actions. So if we were to write it out here, any of these UKs, what it would do is it would look at the possible values of xk. Now xk's can't be fractional values in general. So these has to be some real values, and since a positive and negative are both allowed, these are integer values. That's what the state space is here. And from state space we were going to the action space, and the action space is restricted by this constraint that uk has to be greater than or equal to 0, which means it can be 0. In the worst case scenario, it can go all the way till infinity. Okay, so this is the case for any of these u. I can give the symbol uk also, and it's fine. The point that I'm trying to make here is, for any given action, we need to confirm that action lies in the set of actions that are reachable from a given state. I cannot talk about an action which is not even reachable from my state and include that as a possible uk value. That feasibility check needs to be done, and that's all this condition is trying to say, or this condition is trying to say. Okay, so now we can, so based on the example that we saw and the general framework we saw, we can actually draw a simple diagram to plot like what is the sequence of actions that is happening. So let's say we're focusing on the 0th time step. So at that time step there'll be some x0 value. We can recall the inventory example. Then there'll be some function, some mu0 function that will take in the value of x0 and create a u for us. So a u0 will be created. Some action is taken, or some inventory is ordered, some stocks are ordered. After that, the first randomness shows up in the problem. This is still w0. After all of this is done, based on the dynamics of the problem, the next state will be realized. So next state would be x1, which will be some function. Now this function can depend on which particular time step it is at. Just like in the backlog problem, this function had a form like this. So this function would depend on x0, it would depend on u0, and it would depend on w0. And the same thing will be followed again. So from x1, same thing goes on. We will get an action u1 based on some function mu1. Mu1 is like a plan. If so and so values were there, what should you do if the x1 value was beyond 50, less than 50, if it was in a range between 100 and 50, what should you do in those different situations? How should you take your actions and so on? Next, the randomness shows up and the process repeats and we get the next x2. And this goes on up till xn minus 1. Right, here the process repeats, so there's mu n minus 1, and this is the terminal state. So there's no further from here, there's no further actions to be taken, there's nothing further to happen. The process, the control scenario ends with this. So here there are 2 points that are to be noted. One is, what role is this UK playing? It's doing 2 things. One, that one is fairly obvious. This UK chooses the action for us. So it chooses our action. If the strategy is different, the action chosen would be different depending on whatever xk is actually seen. Another thing it does is it gives a probability distribution. So we can recall our previous example. These w's, either w0 or w1 or wn minus 1, these were the source of randomness in our new state. This is deterministic. The function will have a form, a fixed form. So in that sense, this is all going to be deterministic, but how w0 plays into it is something that will be the core factor. But which action is taken is affected by this function. So the next state, how does that depend on the previous state, has a randomness coming because of this w0 and also because of the choice of the function itself. So this function mu0 or mu1 or whichever one we are talking about affects the distribution of the current state given the previous state. So it is denoted with the pi symbol to represent the whole policy. It affects the probability of getting into a particular state. What are the chances of getting into that particular state given the previous state? Recall, this is affected by two things. One, definitely the strategy. Another is the randomness in the problem. Both of them together are affecting the distribution. But for now, we're only focusing on what is the role of the strategy here. So, is the framework clear? Now, I'll talk about the other way, the second type of framework, which is called Markov decision process. In the previous case, we had the dynamics very clearly defined for us, and it was in terms of an explicit function fk. We saw in that example also. It doesn't have to be in this particular form all the time. In fact, it can be more general, and it can come from a probability distribution, that given xk, with what probability I'm going to reach state xk plus 1, or am I going to reach some other state with some probability. So where am I going to reach can be probabilistic and not be given by an explicit function. So the randomness could be implicit in the problem itself in the form of some probabilities, some transition probabilities, and so on. So I'll talk about the MDP setup, and finally we'll compare the previous setup and the MDP setup, and that conversion between those two is possible. Okay, so in the MDP setup, just like previously, we have some states. Now, here we are specifically talking about the scenario where the state space is finite. The framework holds, it's just that the kind of algorithms that are needed for infinite state space or action space are a bit different and trickier to handle. The framework will be, it'll be possible to translate the framework in those settings as well. Okay, so this is the state space. AS refers to the action space for the state S. So the action space is restricted to the particular state we are at. Next, this RT is the reward function. Remember, this is like more like a comparison. In the earlier setup, the goal was to minimize some cost. Here, the goal is to maximize some reward. So the reward is generally a function of the current state and the action taken from there. So okay, let me take an example at this stage. So think of this scenario. This is a simple Markov chain. Okay, the states here are 0 and 1. These arrows that I've drawn, these ones, they refer to going from one state to another, and they'll have a probability associated with them. So there'll be a probability of going from state 0 to state 1, and then there'll be a probability of going from state 1 to 0. There'll be a probability of staying in state 1 itself. There'll be a probability of staying in state 0 itself. All of these things will be there. So here, okay, let's draw this. Okay, let's say the probability of going from 0 to 1 is 0.6. So what will be the probability of staying in state 0 itself? What will be the probability here?
0.4.
It'll be
0.4.
exactly. So we are looking at the probability of the particular state, and that's what we are summing over. So correct. Similarly, let's say the probability of going from state 1 to 0 is 0.3 here, and hence to stay in the same state would be 0.7. So apart from this, they'll also have a reward attached taking a particular action. So in that sense, this RTSA basically refers to reward at time t when the current state is S and action A is taken. Now here, in this particular way of defining it, we are not focusing on where it is going. Typically, it could also focus on which state is the next state, and hence the reward is defined. For example, in this particular example, red, whatever I'm writing with red in this particular diagram will be the rewards, okay? So my reward from going from state 0 to 1 following this action, well actually there's only one action, is let's say 5. And staying has, let's say, a lesser reward of 2, and similarly some other values elsewhere. So the way I've drawn it here, it's referring to at any given point of time the reward is specific to the initial state, the final state, and the action chosen. We don't always have to go this way. It can be only based on the current scenario also. So what that would mean is, suppose from 0 itself there were 2 ways of going to 1. One is using the red path, the other is using the green path, and the probabilities were different. So here maybe the probabilities were 0.5, or maybe green was with a probability 1 itself, and it may have a different reward. The reward may be 4. So this would mean RT of SA would mean we are focusing on where this action leads. We're not focusing on where this action leads. We sort of take a sum over all of them. I'll actually in fact come to this in a slightly better way. So this means we are looking at, let me call it R tilde. We know that there is a probability, the transition probability of going from this state using this action and ending up at this state. We have a transition probability for that. We have values for that. So if we use those values and sum over these S dashes, the next states, what we get is this kind of a reward. And this is the one that we generally have in our MDP definition. But both of these rewards are fine. You can go from one to another easily. Okay. So let me come back here. So this quantity refers to the probability of going to a next state. Let's say the next state has some name. Let's call it S dash. then the initial state was S. Initial state was S, and action taken from state S was A. And this is all happening at time t. And again, there's a time horizon. We're still talking about a finite time problem. Okay, and similar to cost or reward in the previous problem for the terminal state or the last state, here also we'll have a terminal reward. N being the last state refers to the terminal reward. Okay, so this is the MDP formulation. Any doubts so far?
In this case, P of T, whatever diagram we have given, there one probability is an example or it is actually
Just an
possible?
No, it's actually possible.
Possible, how?
It's possible.
Because the sum of probability will become 2, right? From 0 to...
Oh, right.
It's an only example, right? It's not possible.
1 second. No. So, look at it this way. I am focused on starting at some state and a given action. The action is specific. It's this guy, you'll be putting the standard probability constraints on, that the sum of this over S dash should sum up to 1. But it is at a given action. So here I'm referring to two different actions. So I should have written it more clearly.
So green and blue are two different actions.
Yeah. So blue is action A1. Let's say green is action A2.
Okay, then possible, yes.
Yeah, then it's possible. Not with the same action, obviously. With same action, it doesn't even make sense to go from the same state between two states with two different probabilities. You could just put them together. It doesn't make sense to do it this way. It's different actions.
Okay, then I can say that A1 is possible for state 1, allowable action for state 1, but A2 is not allowable. For state 1, sorry. Because there is no arrow going away from the, so if I reach in state 1, I can't take action A2, so it's not allowed.
So right now I've not made a Markov chain that is, perfectly ergodic and irreducible. Right now I've just made something to make a point. Typically when people talk about these type of problems, they have a few constraints on the Markov chain itself. It has to satisfy certain properties, like you should be able to go back again. There should be some probability of going back, of staying in a particular state. Here with 1, it's just pushing it here and then nothing happens further. So with action A2, 1 actually becomes the terminal state, because you can't go further from there.
Okay.
With this action you can't, but you can always take the blue action here and blue action here, and you can still be in the loop. But what is happening is, this state, if you were to choose this action, you know exactly where you will be. So this is just a fairly deterministic action. The action makes it obvious where you're going to be, what your next state is going to be. On the other hand, this is not telling you. With the blue action from 0, you could be at the same state, or you could change the state with some probability for each.
Nice. And just last thing, this R of T, in this diagram, I can drop T, right?
So right now I've just made the Markov chain, right? I've not written what happens at each time step. The time step could be where am I, which step am I at, and so on.
But the reward still constant, right? So
It can change.
it can change.
It can change. Yeah. That's the reason we have a subscript here. Even the probabilities could change, right? The transition probabilities. The simplest setting is they don't. If they don't, that's the simplest setting. But in the real world, we know these things can change. Mapping them and then studying from them could be mathematically hard. But for a framework, the framework should be general enough to handle different types of situations, right?
Yes, because if you closely see, the reward is a convex hull of, because probability is 0 to 1, so I can consider the convex hull and all this thing.
Sure.
It's very complicated to be.
Sure.
Yeah. Thank you.
Yeah. Next. Okay, actually, I've already made the point that I wanted to make. Another variation is this one. We already talked about this variation, so I'm just gonna skip this part. So, the point to make over here, the overall situation is an MDP is something where we have the definition of time, as in if there is a time horizon, T is that, there's a state space, there is the actions corresponding to each of those states S in the state space. Then there are transition probabilities from one state to another given an action, and there are rewards at each time step depending on which state you're in and which action you're taking. So now let's compare the two different frameworks that we have. One framework is the stochastic control framework, the other is this MDP framework. In this MDP framework, what we have is xk plus 1 is decided based on a probability distribution. On the other hand, in the earlier framework, this is the MDP framework. In the earlier framework, the xk is decided based on some explicit function. That function could depend on all the parameters that are known up till that point. So what we can do is we can write out this probability in a cleaner fashion. Let's say we're calling this state as J. And let's say J is equal to then the transition probability of getting to state J given xk and uk can be written using this dynamic function that we have of evolution. And in this dynamic function of evolution, it's the choice of the function fk that is important and what particular randomness is there. Otherwise, these two quantities are already known. So if we go back to our previous example of inventory, this inventory example had the exact form was xk plus uk minus wk. Now if you're saying this value is equal to some j given xk and uk, if these two quantities are given, the only random quantity in j is wk, then this ultimately is just a probability distribution on wk given xk and uk. So clearly it depends on what form of the function is being chosen and obviously what is the probability distribution on top of the randomness wk. So the point is we can go from one version to another depending on how clearly we have defined our dynamics of transition. If the dynamics can be explicitly defined and can be easily written out, it is possible to go from one version to another. We can go from the stochastic control version to the MDP version easily.
But one more difference, right? MDP state you mentioned it should be a finite state, and there was no constraint over the earlier problem.
That
It could
is
be
that is the constraint we are putting right now. It doesn't matter if the state space is finite or not. The only catch is with finite, we can come up with good algorithms which are possible, for which we have good convergence and so on. With infinite, it's just a little bit harder because we'll have to approximate to be able to calculate and make computations. The framework actually holds for both. The constraint, even while I was saying it here, even when I was saying it here, I was just reminding you that this constraint is only applicable when we are talking about algorithms. In the framework, there's nothing stopping the state space to be, it doesn't have to be finite, it can be infinite. All of these things, just like that, fall through. We have to make certain changes, but it's still possible. The framework holds. The For example, what would change is we will not be able to draw a Markov chain to talk about each state. The states would be so many, infinite, so we can actually make a Markov chain and talk about each of those. So that's where the difficulty will come, but nevertheless it's possible.
yeah. Okay, thank you.
Yeah, so just like before, here again, if we were to talk about the goal, the maximizing goal, again there are no constraints of given st or given the state. It's over the whole thing, meaning we are actually interested in the strategy or the decision rule. In this particular setting, the decision rule is starting from the state space S, it goes to the action space. The action space, because we have defined the action spaces in a specific way, which is for each state small s, we have the action space. So we need to take a union of all those to talk about the decision rule. This one. Same thing as before, nothing changed at this point. Uh, just like before, so now so let's say we are talking about the state st. So the decision rule at st will give us some action to be taken over there, and this action should belong to the action space of st. That's the accessibility part, so that's also same. And here, if we write out all the decision rules, we would have a policy defined as d0 d1 till whatever time horizon we're referring to. Okay, now in the lectures, they talked about types of policies and so on. I'll come back to this in a minute. I'll first take two more examples so we go through it slightly peacefully, and then I'll come back to these policies, the different types of policies. Okay, so slight change here. uh, yeah. Okay, so now consider this example. The only point of showing an example like this in the form of a Markov chain is to highlight what is what and how people typically write an MDP. How do they draw it? How do they visualize at least a small one? So here, if we want to talk about an MDP, we need to be able to define all of these quantities, right? We need to have some time horizon, what is the state space, action space, the transition probabilities, and the reward functions. If we have all of that, that will define our MDP. So in this problem, we have our state space consists of S1, S2, and ST. Before we go any further, based on what we understand by the terminal state and what is visible here, can you see that ST should be the terminal state? A terminal state is something which once reached, there is no further action that is possible. If we have reached this state, no further action will be taken by any policy, any strategy whatsoever, and you'll just have to stay in that state. Nothing further changes after that. That is exactly what is happening here. After reaching this state from either the red action or this dotted blue action, nothing further can happen. There are no self loops or some transitions back to any of the previous states. None of that is possible after here. So this is like a sink, the terminal state. Okay, next, now that we have the state space, we would be looking at the action space. Action space is for each of those states. So what is the action space for S1? The actions available are either to go here or stay here. Both of those are the red actions, or to take the blue action and with full probability 1, go to S2. So the action space consists of two types of actions. One is this dashed action and the other is this action. And this is actually true for all of them. This is true for both S1 and S2. So this is the common one. And there is no action space for ST, which is why it is called the terminal state. So that's fair. Okay, and in the description of the problem itself, here as a tuple it's given the probabilities and the reward. So we have the transition probabilities and the reward directly available from here only. Obviously the rewards that are given here are of this form. There are S, A, S dash. And we know how we can go from here and calculate the reward for SA. The way this one is defined, the rewards are not changing with time, so there's no need for a time dependence here. If they were changing with time, that would have been written out in the example itself. Okay. Now at this stage, we've not seen any algorithms or anything further, how to solve this, how to take actions, how should we go further and so on. So I'll not go into all of that. The only thing that you should notice here is from each state, meaning from S1 and S2, it is possible to reach state ST in finite steps. At least with some probability, with some finite probability. And similarly, with both the kinds of actions, it is possible. So, to be able to solve any MDP, and if we want it to be something that ends at a certain time, this should be possible, that we should be able to go from any state to the terminal state using any action. It should end there. Otherwise, if there is a subsection of the Markov chain which never goes to the terminal state, then there is a possibility if we reach that particular subsection, we might just get stuck there, and instead of it ending, having a fixed time horizon, it might become a infinite problem. Okay, so this is like a very informal way of saying that we want our problem to be with a finite horizon. So this is one example. This is a diagrammatic Markov chain based example. Now, I can show you one more example. This is a bit more real world type example. Controlling a helicopter. Suppose the task is develop a simulator. Using that simulator, finally make a helicopter drive on its own. So, a self flying helicopter rather. And let's say the first task we wanted to do is hover at a place, meaning reach to a certain height and then just stay at that height roughly. Maybe move a little bit, but not too much. So, this problem was studied by Andrew Ng in 2003, and this was basically learning to control a helicopter. So, this particular problem was modeled as an MDP. And like we said, to model anything as an MDP, we need these 5 things. Now, if you think about it, this is a problem with infinite space, infinite state space, and action space. Even if we don't go into details, we know a helicopter can go almost anywhere. So, space available to it, the state of the helicopter is infinite. It can go anywhere. It can, if it changes the value, the position by a fractional amount, even that's a new state. So, even though this is a not a finite state space problem, this can still be mapped into an MDP, and it has actually been worked out. Okay, so now in this particular example, what do you think are the things that are required to define the state of the problem?
Orientation of the helicopter.
Okay, orientation is one. So orientation would be a 3-dimensional object. So orientation.
Roll pitch or maybe XYZ, anything.
Yeah. So let me just put them by some symbols. Okay, theta, phi, and omega. Omega here is some orientation angle only. Okay, what else? Is that enough?
Is this speed, but since it's a hover only, speed is not required, right?
Yes, but it has to reach a certain speed, right? It has to reach up till there.
Okay.
So it has to uh, at least
So then,
move for some time. So during the initial stage when it is moving and reaching at the top, at that time
okay,
velocity will be there.
then it means transient state, and then final steady state will be my terminal state.
Huh. Sure. So you're trying to reach the terminal state. Fair enough.
Okay, okay.
So like you said, speed, position, all of that is required. So position would be some XYZ coordinates. Velocity coordinates would be the time derivative of all of these. So I'm denoting them by just a dot on top. X, Y, Z. And the orientation velocities or the angular velocities will also be there. So those are so this is like a so this state S is a 12-dimensional vector. Okay. In the same paper itself, they actually talk about a reduced state space, but for now we don't need to go into that, so don't worry about that. Like all of these 12 all of these 12 features are not needed, but nevertheless, what about the action space of this problem?
Up and down.
So up and down is something that can be handled by the thrust or the one of these orientation vectors. Which one is that? Okay, that's I think it's the rotating angle of the top blade. The angle of the top blade. Yeah, I don't know what it is called.
This
Pitch
will
angle or
be,
something.
yeah, omega, I guess.
Is it omega?
I think depend upon omega
Let's just write it as the up down motion, but it's because of some angle. I can't recall what is the name of that angle. Yeah, what else?
And maintain that, like if you reach in terminal state, you need to maintain that. So action could be like to
Action could be like?
To maintain that thrust or whatever angle which is stable, like stability.
Okay, so maybe like the back tail rotor could keep rotating to keep it steady, keep it sort of balanced over there at that particular height and not go any further. Cancel out the upward thrust created by this uh, thrust created by this rotation. So maybe some sort of a balancing act. Okay, apart from this, if it has to go up, it might not always be feasible to go straight up. It's possible that it might drift in one of those two directions, so it might have to come back left, right, front, backward, all of that also. So those two are also to be considered. So front or back and left or right. So there are four actions, A1, A2, A3, A4. Okay, so this model has the following states and actions. Now, how do we talk about fine, we can't really talk about time directly, but we can be like, okay, how about it manages to steady itself in so and so number of seconds or so and so number of minutes. So that can be just randomly set and it's fine. How do we talk about reward and transition probabilities?
Isn't it we need to define randomness source first, or
We don't
directly we
need
can
to
control?
define, we just need to understand what is the source, what causes the randomness in the problem. Okay, so what causes randomness in this problem? What are the factors that would affect?
One thing I'm thinking about weather or air speed.
Right, air speed, so it might cause resistance, it might cause some drifting. So all of both of these are factors. What else?
And then either the petrol or maybe the what to say, the source of energy for the helicopter.
The fuel source. That, okay, that'll keep reducing with time, so they might have to eventually come down and so on. Okay, but I don't think this is a clear source of randomness in either of these tasks, to hover in a place or follow a trajectory. Fuel, we can assume that that is already budgeted and sufficient is available, so that may not be a very big factor.
Okay.
Okay, fair enough. This is fair enough. Thinking of this much means we've already covered the core things that define how a helicopter is to be controlled. Now, let's come back to this point. How do we talk about reward and transition probabilities? Typically, like in the previous problem, this was a constructed problem, so we could actually talk about giving some values to probabilities. How do we go from one state to another? On the other hand, right now what we have is a real world problem. The source of randomness itself is something so unpredictable that we can't give these probabilities by hand. We can just roughly expect in a big enough time frame that if this is the action we are taking, after this much time, this is roughly where we should be. We'll not even be able to give an exact value that this is the exact state we should be in. We'd be able to give a range. So, whatever we end up having, this probability distribution is going to be a continuous probability, not a discrete probability like before. Okay, and reward can be very simple. The reward is as if the correct state is hit, if the terminal state, so exact coordinates of that, or with some margin, if that state is reached in case of hovering, then the reward can be won, otherwise no reward. Similarly, when talking about following a trajectory, if at every time interval the main point of the trajectory is hit, then we give it a reward, and if it is following that, then the reward gets incremental, otherwise no reward, or negative reward if it is going too far away. So distance could be what is used to distance between the state that we want it to be for a particular trajectory and the state it is at. So some sort of a distance measure could be used to come up with a reward function or a penalty for that matter. Okay, but this is still very rough. This depends on how we want to simulate it and how we want to deal with it, which particular task we are dealing with. Depending on the task, the definition could be varied, and changing the definition changes the problem slightly, and hence it will give slightly different learning outcomes for both of them. Okay, so the point that I want to make with these examples is when we are talking about stochastic control or MDP planning, the kind of problems that can be dealt with are not just restricted to inventory or finance or these ones. We can also deal with problems of robotics, problems from CS community, problems from operational research, and so on. So whenever we are talking about applications of this, keep in mind the range is very broad and it can be applied to a huge number of settings. Okay, now let's quickly go back and talk about the different types of policies. So the policy that we've been talking about mostly was the Markov policy. Okay, let me erase some of it and I'll write all of this part again. Okay, so these policies could be of different types. One of those types is called Markovian, meaning we start from some state, we take the information of the state S and choose an action. So in this particular case, dt is dependent on just the very last step, nothing more than that. Another possibility is, so this is one, this is the second possibility, that it depends on the history. History could be something that includes the state and the action up till the previous time step and the state at that given time step. So if we were to write the whole set, okay, the set of all the history, that would be denoted this way. This done almost t times. And finally the tth state, which means H0 is just S cross A. Oh, no, not even A, because A would not have been taken. S1 would be S cross A cross S. And so on. We can go further and continue talking about this. This is the set of all histories. Any policy which is history based will start from the space of histories or the set of all histories and go to the corresponding actions. So image is denoted by A. Okay, meaning for that particular dt we would have all the previous history as the parameters inputted in it and use that to get the correct action from the action space of st. Why st? Because we are finally taking the action after looking at this state, and because the action space is defined with respect to each state, we'd only be looking at the action space of the last state. We won't look at the action space of all of these states and so on, the ones previously. And this should hold for different these parameters. Okay, so that is this. So if we were to look at the first one, the Markovian, we could say the policy, the set of all Markovian policies. Let's say we denote it by pi m, and the set of all history dependent policy is what we denote by pi h. Then what will be the relation between these two? It's clear to see that Markovian is a special case of history dependent policies, which means the set of Markovian policies should be a strict subset of history dependent policies. It's only in very rare cases that there might be an equality here, that these two spaces are same. Typically it won't be. Apart from this, there could be stationary state also. Stationary state just means these functions d0, d1, all of those till dn minus 1 will be the exact same function. What they are taking as input may still vary, and hence what they create as actions might still be different. But the form of the function is same. The function doesn't change with time. If that is the case, we call those as stationary policies. Okay. So the relation between these three now is stationary policies are a special case of Markov policies, and Markov policy is a special case of history dependent policies. But these are all policies where the result of these functions, these D policy functions, this or this, whichever one we are talking about, or even the stationary one, gives us only one action. But it's not restricted that there has to be only one action. It's the action also can be randomized. So if the action itself is randomized, if this is how the situation is, starting from a state, we get more than one action, and each action comes with some sort of a probability distribution on top of that. Then we have another set of policies that come up, and these policies are called randomized policies. So here this refers to the probability distribution. One second. or rather the set of all the probability distributions. This is a specific probability of being in state of taking action A under policy dt from state st. Okay. Yes, what was the question?
Okay, so if we go with any other model except randomized policy, the source of randomness is a transition probability, like how things are transitioning. Okay.
Yes.
But here in this case, I'm creating a new like randomness in the system. What is the advantage we will get out of this?
So it's like saying, take the example of stocks. Okay, you can buy stock number A or you can buy stock number 2. One has so and so possibility of giving you profit and so chances of having a risky investment, and similarly for the other one. If you randomize over the two, as in you put a fraction of your money in one and fraction of your money in the other, you're getting a trade-off between risk and the benefit you get. So that's something similar will happen here also.
Okay.
So people talk about randomized policies when there is a benefit of doing a randomized policy. Randomized policies are not always useful, but it is good to keep it in mind using the lottery example.
Okay.
Okay, so now I'll just give quick definitions. I think we're almost over time. Similar to the previous case, we have Markov randomized policies. This can be stationary if this function q does not depend on time. So this could be the set of stationary randomized stationary strategies. And last, we could have it history dependent. So just like we had relations between the regular ones, the deterministic policies, we could have similar relations between these also. So those similar relations would be, so we had this relation, right? S was a subset of M, and that was a subset of the history dependent one. Exact same will be here in this case also, in the randomized case also. Apart from that, if we talk about a Markov strategy and its randomized version, randomized is always a bigger set of strategies than the non-randomized one, because deterministic is a special case of randomized. Deterministic is just where the probabilities are given as 0 and 1, zeros and 1. So in that sense, this is always the case. This is true for M, this is true for S also. This is true for histories also. Randomized histories. So this is the full set of relations we have. Okay, so these are the relations between the different policies. So today, let me just do a quick recap. We talked about stochastic control. We looked at the formulation. We talked about what is open loop and what is closed loop. And we said that throughout this course, we're actually going to focus on closed loop problem, which means that each action UK will be something that depends on the state xk. Then we talked of one particular example of inventory control and what kind of variations we can come up with in the same problem. Then we finally talked about the Markov decision process, how this is slightly different from the previous formulation. We saw how we can compare the Markov decision version with the earlier stochastic control setup that we had. And whenever we are trying to reach our goal, minimize or maximize some cost or reward, we are actually not taking any conditionals, meaning we are not taking these decisions one at a time. This is a full set that is taken together, and hence the focus is on coming up with the plan of action for different type of situations, which is why our focus is on strategies and not just actions. Then we talked about the different types of policies, and we saw that finally the relations between the different types of policies are the following. There can be equalities in special cases, but typically this is how it is. And last, we saw a few simple examples of MDPs. This was one which was like a actual Markov chain given to us with the probabilities, the transition probabilities, and the reward model on top of it. And we also saw a real world example of how